All right, now today we're going to be looking at a really fun topic called implicit differentiation. Now we've already covered how to do first derivatives and what the power rule looks like, but let's take a look at that one more time. So let's assume we have a function f of x equals, let's just say 2x squared plus 3x plus 5. Now, when we take the derivative of this, we notate it with a prime on the f. And now remember, we drop this power by 1, and we multiply the old power by the coefficient. So what we get is 2 times 2, x to the 1, plus, now this x has a secret little 1 up here, so we get 3 times 1 times x, and then the 5 goes away entirely. So our solution becomes 4x plus 3. And notice that when this one comes down, we actually get a little 0 up here, and anything to the 0 power is automatically 1. So that's why we get this 1 here, and the x actually completely disappears. Now this is really cool for any functions that we have y on one side and x on the other side. So we have things that have y equals f of x, and then we just have a bunch of x things over here, like exactly what we had listed up top. But here's the problem. When we actually do math, when we look at functions in real life, one of the problems we have is that we can't always pull y and x away from each other. That's not always a feasible thing. So with implicit differentiation, what we're able to do is we're able to actually differentiate functions where the output and the input are intimately intertwined. So let's take a look really quick. Let's look at another function. Let's say 2y plus 3x equals y squared. Let's leave it there. So when we do implicit differentiation, what we're actually doing is we're applying an operator. We're applying the d dx operator to this entire thing. That's how we take derivatives. Now, one of the things we need to keep in mind is that differentiation is linear. That's a very important property because what it means is that we can actually multiply it through to each of these, and things like association and commutativity actually apply with differentiation. Now, linearity is a property that we won't get into anywhere in this class, but it is interesting to note that a lot of calculus operators happen to be linear. So what we can now do is we can actually distribute this d dx to each of these terms. So we get d dx times 2y plus d dx 3x equals d dx y squared. Now here's where things start to get interesting. What we need to remember over here, one of the things that makes this as unique as it is that y equals some function of x. Okay, y isn't like when we have x on the other side and we can just drop the powers. We need to remember that there's actually x's in here. So if I was to tell you that I had a function, and let's actually move off to the side for just a minute here. Let's say I told you that you had a function y equals f of g of x. Now, from previous chapters, one of the things we've learned is that y prime is going to be f prime g of x times g prime of x. And if you remember the terminology, what we called this thing the chain rule. Now, the chain rule is important because we usually have functions and functions. Compound functions are things that we encounter all the time in mathematics. And this chain rule gives us the ability to deal with functions that have that, right? So what we're actually looking at when we're over in our previous example for implicit differentiation, what we can actually notice is that this y here is an f of x. So this 2y is a function in a function, right? Because this 2y is a function. It's an f of x. And then the y we could call g of x. And boom, right away, we have an instance where the chain rule is directly applicable. Okay, so let's look at what we would have if we differentiate the outside. Well, 2y is just going to be 2, right? Because the y drops away. But then we have to remember that we have to multiply it by the inside function. So we get y prime right here. Now let's look at this one. Well, since this x, this dx, and this x, that has the same variable, this is just one function. So we don't have to worry about chain ruling. We can just call that 3. Then over here, we can drop it to 2y, but we have to multiply it by, by y prime. Okay, so this component, these components here, are what actually complete the chain rule in this operation. And that's very important to know. Because if we didn't have that, it would just be normal differentiation, and we'd end up getting the wrong answer. Because this variable down in this differentiation operator is not the same as what we have in our function. So are we done? Well, we're not completely done, but we're getting pretty close. We're pretty solid right now. So what we need to do is now we got to clean this whole thing up. Well, what are we trying to solve for? Well, when we ask to differentiate it, what we want is if I have a function, and let me put this in a new color. If I have a function, y equals f prime of x, and I ask you to differentiate it, well, the answer is going to be in terms of y prime or f of x prime, right? So we actually need to get y prime all by itself. So let's just rewrite the function in here. We got 2y prime plus 3 equals 2y times y prime. Well, we got to use basic algebra skills here. So what's the first thing we're going to do? Well, we're just going to move this 2y to the other side. So we get 3 equals 2y, that should be not a squared. I'm probably going to make that mistake this entire time. Y prime minus 2y prime right here. Now let's move up here, give ourselves a little bit of space. Let's keep down here and save that for a little later. And what we're going to do is we need to factor out a y prime from here, because that's what we're trying to solve for. Now, since these are two different terms, we can't just add them or subtract them. So that's where the factorization comes in. So we get 3 equals. Now, pulling out a y prime, we're left with a 2y. And pulling out a y prime, we're left with a 2y prime. Well, now the operator between this quantity, this 2y minus 2, and this y prime is multiplication. And as we know from algebra, but we're going to solidify here, we're going to recall that the opposite operator for multiplication is simply division. So I need to divide this by the thing I don't want. Well, the thing I don't want is this on this side. So we're going to say 3 over 2y minus 2 equals 2y minus 2 y prime over 2y minus 2. So these two quantities immediately cancel, and we are left with 3 over 2y minus 2 equals y prime. Now, one of the things we can notice that's kind of funky about this whole situation is that in our original function, let's go back and let's see here, we had 2y plus 3x equals y squared. And down here, we have a function that is purely in terms of y. We don't have an input in here at all. It's kind of weird. The differential, the derivative of this function y is solely determined by the behavior of the output. Now, of course, the behavior of the output is ultimately determined by the behavior of the input, but still, that is interesting note in here. Now, one of the things we do have to be aware of, not just how to use a tool, but when do we properly use a tool? Okay, let's copy down the original question. So we had 2y plus 3x equals y squared. So let's put a nice little breakpoint here. And we got, and I already forgot, would you look at that? 2y plus 3x equals y squared. So we got 2y plus 3x equals y squared. Now when we applied the differential operator, we saw how to do that. But how do we know that we need to use implicit differentiation to do this? Well, the key here is that when I give you something that or a textbook gives you something that you just need to straight differentiate, it's going to be in this form. It's going to be y equals f of x. And y can be contained over here. Well, what's the problem with this one? Well, let's do a little manipulation. Let's move all the y's and the x's to their appropriate sides. So we get 2y minus y squared equals negative 3x. Actually, let's rewrite that. That's honestly, and this is a mistake that I make just like everyone else. Sometimes I overcomplicate. Let's actually just subtract this over and then flip the two sides. So we get y squared minus 2y equals 3x. Now, it's a problem here. Well, we can't actually combine these y's. We can pull a y out, and, well, that's really all we can do. We can pull a y out, and we could factor it, but we'd still be left with two y terms no matter what we do. We cannot get it in this form to simply find a y prime. So what we know is that when we see y's that are of different powers, we have to use implicit differentiation. One of the other times that we often use differentiation is also when we get things that have x's and y's multiplied together. And that's because when we divide the y, oftentimes it creates a bunch of problems that we can't algebraically solve for y. So we have to use implicit differentiation. Let's go over one more example here really quick. Let's just kind of get our feet under us. Let's just do a fun little example to kind of close out our little lesson here. So the function we're gonna look at right now is we're gonna look at xy squared minus 5x squared y equals y cubed plus 3x. 3x is showing up again. I like 3. I like x. Sue me. So let's apply the differential operator. That's what we're going to do. We're being asked to take the derivative. Now, because differentiation is linear, we can just apply this differential operator to everybody. So let's just go ahead and do this. And one of the reasons I like to actually notate this is because later on in mathematics, one of the things you will run into is having to manipulate operators solely by themselves. I've read math papers that are completely covered in nothing but these operators. There's no actual numbers or letters. There's nothing to differentiate. They give you maybe a y and maybe an x, but it's about the manipulation of these operators. So knowing how these operators behave gives you some very deep insight into the things that you can eventually do with the operator and the process that it describes. So let's go through these one by one and let's just differentiate these. Okay, so we already have run into a problem with the first one. What's our problem? Well, we have two functions here. X, you could write as f of x, and y is going to be a function in a function because y is determined by some other function that we don't know because we can't solve for y here. And then there's a function outside that's going to be the squared component. So when we have a function multiplied by a function, we go straight to our product rule. So what's our product rule? Well, let's go down here and let's look at the product rule briefly. So the product rule is going to be f prime of x, g of x plus f of x, g prime of x. Okay,
So now that we have our product rule written down, we can go through and, well, we can say x is going to be f and and y squared is going to be g. So the derivative of x is 1, and we leave the y squared alone. And now in this case, we leave the x alone. Derivative of y squared is going to be 2y times y prime. Just because we use the product rule doesn't mean we can skip on the chain rule. Now let's move on to the next one. We get, and I'm actually going to rewrite this slightly lower so we can leave ourselves plenty of room. Y squared plus x plus 2y y prime minus. Now the 5 is actually going to come out, and we get 2xy plus x squared y prime. Why just y prime? Well, because the derivative of y is y prime. And if you want to look at it like the chain rule, well, we bring the 1 down. This becomes a 0 up here. That becomes an immediate 1, and we multiply it by the derivative of the inside, which is y prime. And why did I pull the 5 out? Well, because it's not attached to this one or this one. It's actually attached to both of these. So constants, we need to remember, we need to pull out what we can when we do the chain rule. Or excuse me, the product rule. So now we differentiate this. The 3 comes down, becomes a y squared. Don't forget that times y prime. Plus 3, and the x goes away just like a normal derivative. So now we just need to make this look a little prettier. So we get y squared plus 2xy y prime minus 10xy plus 5x squared y prime equals 3 y squared y prime plus 3. Okay. Well, just like our first example, we were asked to find the derivative of y, so we got to get those y primes all by themselves. So we get 2xy y prime. That's our first one. Then we get plus 5x squared y prime minus 3y squared prime equals. So now this y squared and this have to move to the other side. So we subtract them and we get negative y squared plus 10xy plus 3. All the y primes over here, everything else over here. Good. Now we can pull out a y prime. So we have y prime 2xy plus 5x squared minus 3y equals negative y squared plus 10xy plus 3. We are in the home stretch. Now, last step, you guessed it. Simply divide this entire side and this entire side by whatever we don't want. So it's whatever's left over after factoring out the y prime. So in the end, we get y prime equals negative y squared plus 10xy plus 3. That all stays in the numerator. Then we end up with 2xy plus 5x squared minus 3y. Beautiful. There we have it. We have now implicitly differentiated a function. Admittedly, a pretty gross function, but a function nonetheless. And we were able to do it using calculus rules that we've already learned. Simply the chain rule and the product rule and the power rule. Those are things that we've practiced a multitude of times, but are going to be tricky in this new context because one of the things with implicit differentiation that I think is very, very important is knowing when to apply it. And notice, let's go back up and let's look at our original function really quick. Let's see. Notice this met the criteria for using implicit differentiation. We had a y squared, we had a y, and we had a y cubed. So when those y's are different powers, we have to use implicit differentiation because we cannot find a simple algebraic solution. It's just not possible. However, there are certain times where you could probably factor it and then find different functions. However, that type of process is going to be much more difficult to apply than implicitly differentiating. This process also works for trigonometric functions. When you have y's trapped in trig functions and you can't explicitly solve for them, implicit differentiation, you can knock that right out of the park, no problems. So that's about it covering implicit differentiation. If you have any questions, please feel free to contact, email, or via your other available platforms to get a hold of me. I will be posting a couple more examples on this later on. I just want you guys to get a feel for it. Go ahead and try some of those problems in the book, and I'll see you guys next time.